So today we're going to cover section 8.7 in the book, going over epoxides. So we've just gone over reactions of ethers, and so now we're going to go into what we call cyclic ethers. So we had just been talking about acyclic ethers. So what that means is the ether, the two alkyl groups attached to the carbon were not connected in a ring. Cyclic ethers are molecules where the alkyl groups attached to the oxygen are connected to each other somehow. And just so when the cyclic ether is a 5, 6, 7, or 8 membered ring, the reactivity and the physical properties and the chemical reactivity of acyclic ethers, or of the chemical properties and physical properties of cyclic ethers, mirrors the chemical and physical properties of acyclic ethers. So what that means is that if we were to take, what that means is that these molecules are generally unreactive, which is why they're commonly used as solvents. So 1,4-dioxane is a common solvent. Tetrahydrofuran is a common solvent. And because they're common solvents, because they're unreactive, they're used in a number of different reactions. One of the reactions that can take place is you can react these with HX to break the carbon-oxygen bond in the same way as with cyclic ethers. Now, we're going to focus in this section on something that we call an epoxide. So an epoxide is a molecule where the cyclic ether is a 3-membered ring. So you have 2 carbons bound to an oxygen. So it's a cyclic ether. And because it's a 3-membered ring, the chemical reactivity of this molecule changes drastically. It's much more reactive. So this goes by 2 different names. These molecules are called oxiranes. So where that term oxirane comes from, IR comes from tri. So in the oxirane, this IR comes from tri, meaning 3. Ox for oxygen, and then ane for a saturated molecule. So a 3-membered saturated molecule with an oxygen in there. So that's an oxirane. Now, we also call these epoxides, and that's how we're going to talk about them. And we're going to refer to them as epoxides. Now, because the epoxide is a 3-membered ring, there's a massive amount of ring strain here. That massive amount of ring strain increases the reactivity of epoxides. Now, the way you make epoxides is you take alkenes and you react them with a peroxy acid. The most common peroxy acid that we use is something called metachloroperoxybenzoic acid. It's usually abbreviated MCPBA. So when you see MCPBA, we're doing a type of reaction called an epoxidation. So this is where the double bond reacts with this electrophilic oxygen to make a 3-membered ring. Now, the reason why this is called a peroxy acid is because this looks like peroxide, and then this kind of looks like a carboxylic acid with an extra oxygen. This molecule is really interesting because when you make this molecule, this oxygen becomes very electrophilic. So what happens here mechanistically, and I'm not going to expect you to know the mechanism, but I'll just draw the mechanism for you to kind of give you a sense of what's thought to happen here. So when you have these peroxy acids, this oxygen here is the electrophilic oxygen. The double bond, the alkene, is nucleophilic. That's usually the case. So the double bond is going to attack that. The bond between this oxygen is weak. So when you have a covalent bond between 2 heteroatoms, that bond is usually relatively weak. That's going to break this bond. That's going to push these electrons up here to take that proton. And then these electrons between the carbon-oxygen are going to attack one of these carbons here. So this oxygen gets attacked, and then these electrons attack one of the carbons to make a 3-membered ring. And so you make the 3-membered ring. This is a syn addition. So what that means is all of this formation happens on one side of the alkene. So the 2 bonds of the epoxide are going to be facing the same direction. And then the byproduct you make is a carboxylic acid. Once you have these epoxides, so they're relatively easy to make. Once you have these epoxides, they're very reactive. And so let's look at the reaction with HX. So this epoxide is going to react very similarly to how HX reacted with the acyclic ethers. So remember, when you have HX or some acid, so the acid could be in the form of HX, it could be in the form of H2SO4, sulfuric acid, HCl, H3PO4, H plus, or even H3O plus. These are just a small sampling. But any of these things, when they're used as reagents, the first step is almost always a proton transfer. So we have HX here. And so this molecule of HX is going to be a proton transfer. So this means that this is going to be my acid / electrophile. I need to find something nucleophilic. It's going to be the oxygen. So a lone pair on the oxygen is going to attack my hydrogen, kicking out H minus. What that's going to do is that is going to make the oxonium here, and that's going to make this molecule now even more electrophilic. Or now my electrophile is this molecule here, the oxonium. And remember, it's not the oxygen that's electrophilic. This positive formal charge on the oxygen makes that oxygen more electronegative, making the carbons attached to that oxygen even more electrophilic. So what's going to happen here is when you attack, you have X minus. So this X minus is a nucleophilic. It's going to attack my electrophilic carbon. This is an SN2 reaction. So this is going to approach from behind this carbon-oxygen bond and open up this ring. So what that's going to end up looking like is it's going to end up looking like this. Okay? So the product here is the opening, and if you kind of go back and you look at it, this product is related to the acyclic opening, right? So in the acyclic opening, the difference here is that these two carbons, in the ether, these carbons aren't attached, right? Like this carbon and this carbon aren't attached. So one of these carbons would become the alkyl halide, one would become the alcohol, which is what you see. But the product looks very different here, right? Because the carbons are attached in the cyclic ether. And because I can attack either carbon, right, I get this molecule plus the enantiomer. The reaction is stereospecific in the sense that these two groups are trans to each other. The opening is trans, but you make this molecule plus the enantiomer. So we can do the same type of reasoning if we react it instead of HX, we react it with H3O plus. So let's see what happens if I react it with H3O plus. So if I react it with H3O plus, remember H3O plus is an acid, and when you see H3O plus, really what's nice to think of H3O plus as is H plus and H2O, water. Okay? So what's going to happen here is I'm going to do a proton transfer, just like in the HX case, proton transfer. That's going to give me the oxonium here. Right? That gives me the oxonium. This carbon's more reactive. My nucleophile is water. So that's what I have, a bunch of this lying around. So now I'm going to open this up here. That's going to open up my epoxide in an SN2 fashion. Again, this is an SN2 reaction. Even though water is a weak nucleophile, this is a very good electrophile, right? Putting the positive formal charge on the oxygen makes it more electronegative. It doesn't want that positive formal charge. So I'm going to open up. This is the water molecule that was added. And then I open up, and I have my OH here. And notice they're trans to each other, right? This still has a positive formal charge. I'm going to get rid of that positive formal charge on the oxygen by regenerating my acid via a proton transfer. And what that's going to give me is the final product, which is a trans diol. So I've made the trans diol here. Okay? And we've actually gone over this reaction already, right? We've gone over this already. So this is just kind of a review of the epoxide reactivity. Okay? So We can open up epoxides with either HX or H3O plus in a very similar mechanism. The difference between the two mechanisms is that in the HX case, in the second step, the nucleophile is X minus, whereas in the H3O plus case, the nucleophile that attacks is water. And you end up with a transdiol when you open an aqueous acid, or you end up with something we call the halohydrin, where the X group and the alcohol are trans to each other. So this molecule is called a halohydrin. Okay. Now we can also react epoxides with a nucleophile, with a good nucleophile. So notice that in these cases, these are reacting under acidic conditions. So what that means is I have HX or H3O plus. I can also open epoxides under what we call basic conditions. So when we have basic conditions, the nucleophile we use it's going to be a good nucleophile. So basic conditions involve negatively charged molecules. So these are going to involve reactions with CN minus or OH minus, OR minus, SR minus, I minus, BR minus. Now, because I'm going to be using a good nucleophile here, such as we're just going to abbreviate all of those good nucleophiles with Nu minus. I have a good nucleophile here, right? And what we're going to think about is this reaction is either going to be SN1 or SN2, all right? So if you kind of go through our flow chart, this carbon's tertiary, right? This carbon is secondary. So let's say I'm going to be with the tertiary carbon, right? I could, if I was going to attack here, if I was going to do something with this tertiary carbon, if you go through your flow chart, the reaction only thing that you could do with a negatively charged nucleophile would be the E2 elimination. But because you have, and these are all good nucleophiles, that's something else to keep in mind. These are good nucleophiles, good nucleophiles slash bad bases. So these molecules that I'm listing here are all good nucleophiles. So because these are good nucleophiles but not very basic, we're not going to be doing the elimination. And what we're going to actually be doing is we're going to be reacting at the secondary carbon. And because we have a good nucleophile, we're going to be second order. And the reaction is going to be an SN2 reaction. So what's going to happen here is, so because this is a good nucleophile, this is going to attack the secondary carbon here. So let's draw the mechanism and the product of this reaction. So what's going to happen here is this negatively charged nucleophile is going to attack the less hindered carbon and open this up right away. Now when it does that, it's going to open that up in an SN2 fashion. The nucleophile that you added is going to be facing the opposite direction as the OH, as the epoxide, right? So both of this bond the nucleophile has to approach from the opposite side of this bond here. So the nucleophile is going to be facing away from you. The O minus that you open up, that's going to be facing towards you, and then that methyl group is still going to be there. That's the first step. So in the second step, when you see H3O plus or H plus or some acid, it's a proton transfer step. So then there's a proton transfer step. So the oxygen is going to attack that proton to give you the alcohol here, the methyl group going away, and the nucleophile going away. Okay? So that's the final product, right? So what's happened here is that the nucleophile has attacked this less hindered carbon in an SN2 reaction, opened up to make the alkoxide, which becomes protonated to make the alcohol here, and whatever the nucleophile here is here. All right, so that's those are reactions of epoxides. Let me know if you have any questions, and I will talk to you later. Thanks. Have a great day.